Okay, everybody, welcome to Lecture Me. My name is Lucy, and I work at the Mississauga Library. It's my honor to be your moderator this evening. Tonight, our program is The Big One, The Where, When, and How Bad of Earthquake Science with Professor Lindsay Schoenbaum from the Department of Chemical and Physical Sciences at University of Toronto at Mississauga. This lecture will explore how and how well we can predict the location and timing of earthquakes. We'll discover what makes some earthquakes so deadly and how to prepare for a possible major earthquake right here in southern Ontario. Before we begin the program, we start with a land acknowledgement. We acknowledge the lands which constitute the present-day city of Mississauga as being part of the treaty and traditional territory of the Mississaugas of the Credit First Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and Wyandot nations. We recognize these peoples and their ancestors as peoples who inhabited these lands since time immemorial. The city of Mississauga is home to many global Indigenous peoples. As a municipality, the city of Mississauga is actively working towards reconciliation by confronting our past and our present, providing space for Indigenous peoples within their territory to recognize and uphold their treaty rights and to support Indigenous peoples. We formally recognize the Anishinaabe origins of our name, Mississauga, and continue to make Mississauga a safe space for all Indigenous peoples. Next, we have a few technical details. This is a hybrid lecture, so we have the people in the room, the live audience, but we also have people who are joining us by WebEx webinars. So we have people monitoring that, and that's why we have the camera set up. For those of you who are attending in person, you won't be visible to the attendees online. You have to be in this sight line to be seen by them. There will be a question and answer session at the end of the presentation, and when you, the live audience, ask the question, Lindsay will repeat your question so that they can hear what it is, because they won't hear if only you say it. I'll be monitoring the chat for questions and comments from the online audience, and if they have questions, I will repeat them so that you can hear them. So everybody gets to share the questions. But please be patient with us while we repeat. So Lindsay will be repeating from live, and I'll repeating what's happening on chat, and we'll hear all the questions together. A few things about Mississauga Library. We want to promote our e-resources. We have so many e-resources. Our 24/7 digital services are available for free with your library card. They're also available from home at mississaugalibrary.ca. We have ebooks, we have magazines, newspapers, movies, music, many specialized e-resources like Mango Languages and LinkedIn Learning. Please visit our website for more details or call us. I'm going to be back for the question and answer session after the lecture, but now James Malinowski will introduce tonight's speaker.
Good evening, everyone. In collaboration with the Mississauga Library System, we thank you for attending tonight's sixth Lecture Me and final Lecture Me talk of the 2023-24 season. My name is James Malinowski, and I'm the Community Engagement Officer in the Office of the Vice Principal, Academic and Dean at UTM. It is my pleasure to introduce tonight's speaker, Professor Lindsay Schoenbaum from the Department of Chemical and Physical Sciences, who will be delivering her talk entitled The Big One, The Where, When, and How Bad of Earthquake Science. Dr. Schoenbaum is a professor of earth science and chair of the Department of Chemical and Physical Sciences at the University of Toronto, Mississauga. She holds a PhD from MIT and was awarded a Humboldt postdoctoral fellowship in Germany. Her research in tectonic geomorphology and landscape evolution examines how tectonic forces build mountainous topography and how erosion by wind, water, and glacial ice tear that topography back down. Her research ranges from the Tibetan, Anatolian, and Andean plateaus to rifted continental margins to earthquake record. She has made a number of media appearances over the years, almost always after devastating earthquakes. So she says it's a pleasure to be talking to an audience about one of her favorite subjects, not in the wake of tragedy, but with more of an eye towards prediction and prevention. She lives in Toronto with her two daughters, one of whom is here tonight.
Okay, so this is a real image from the Tohoku earthquake in Japan in 2011 of a tsunami. So as I was saying, tsunamis aren't quite as scary as they are when they're portrayed in the movies, but they are a pretty serious hazard to think about. So what I'm going to talk about today is, first of all, what is an earthquake? And then what causes them and where do they occur? And then how are they measured? And we'll do this relatively quickly, just in a couple of slides. It's sort of setting up the basis for the rest of the talk. And then we'll spend a bit more time talking about what makes earthquakes so deadly, and particularly why are some more deadly than others, and can we predict earthquakes? And then at the end, I'll talk about what about Southern Ontario. And in case anybody has to leave early or you're feeling very anxious about this, the answer is I don't lose sleep over an earthquake in Southern Ontario. Yes, it's possible. And as we've had an example from this gentleman and my own experience, we can have shaking in Toronto, but it's not likely to be a large magnitude. So something you might feel, but not something to lose a lot of sleep over, unless we get really unlucky, which happens, but we're always weighing risks, so it's okay. All right, so starting off with what is an earthquake? So an earthquake is when strain builds up in the Earth's crust, when the rocks are trying to move and they can't, either because there's frictional resistance along the fault or because they haven't broken yet. So they're accumulating strain. And then when they do finally break, or that frictional resistance fails and the rocks move, it releases that sort of stored strain as vibrational energy. And so the analogy we make sometimes is breaking a stick. You've broken a stick before, and you know how it sort of resists you, and you have to push and push, and then eventually it snaps, and it's a sudden snap, and you can usually feel the vibration in your hands. So that's essentially what happens in an earthquake. Earthquakes happen on faults. So here's an example of what we call a normal fault or an extensional fault. And the earthquakes happen at some point along the faults. We can call that the focus or sometimes the hypocenter. And then you project it up to the surface, and that's what's known as the epicenter. And that you hear a lot because we care about the epicenter because that's where people live. And then the earthquake waves radiate away from the focus or the hypocenter. And just like ripples in a pond that radiate away from the point of impact of a pebble, these ripples in the Earth's interior, they radiate out, but in 3 dimensions, right, through the interior of the Earth. We won't have time to talk about it, but there's different kinds of waves that move at different speeds. Okay, so next topic already. What causes earthquakes and where do they occur? And the short answer is plate tectonics. So not every single earthquake happens on a plate boundary. Plate boundaries are actually really complicated, and you can also get earthquakes in the interior of continental plates. But essentially, it's the movement of tectonic plates around on the surface of the Earth that causes earthquakes. And so you can see that the little dots here on this side are showing where earthquakes occur, and they more or less outline the plate boundaries. So these little guys out in the ocean are usually very small earthquakes, so they're far from people, so we don't feel them. But they're occurring out here where the new oceanic crust is forming. And there's a whole bunch of earthquakes you can see here in this diagram on this thing here we call a subduction node. So this is where oceanic crust dives underneath other oceanic crust or continental crust into the interior of the Earth. And you can see those along the west coast of South America, along in the Pacific Northwest, the Aleutian Islands, Kamchatka, and then all down through here in the Pacific. The dots sort of show the depth. So when you see blue dots, it means you get very deep earthquakes that happen along subduction zones. And these are associated with volcanoes. So this is what's known as the Ring of Fire, if you've heard of that before. This is where the biggest earthquakes happen. These faults tend to be relatively continuous. They're also relatively cold because they've been refrigerated by contact with the ocean. And so you can get really big earthquakes. Sometimes we call them megathrust earthquakes. Those are earthquakes that are magnitude 9 or higher range. And then you can get earthquakes along transform faults. So that's what's happening along the San Andreas and the East Anatolian fault zone in Turkey. And that's a place where the rocks are sliding past each other. It says strikes the fault right up there. And those tend to be more on the order of 7 or sometimes a magnitude 8. And usually that's just because the crust is chopped up a lot more. And so you can't rip a big fault along a really large area. It tends to be a smaller rupture area. Okay, and next I'm going to talk about how we measure earthquakes. And probably everybody has heard of the Richter scale. Yeah. We don't actually use that anymore, at least not in science. And the reason is it does pretty well at lower magnitudes, but when you start to get to higher magnitudes, part of how you calculate it has a logarithmic scale, and it starts to compress things. So it's not very good at measuring large magnitude earthquakes. So what we actually use is the moment magnitude. And it's been scaled so that it corresponds more or less to the Richter magnitude. So they're similar, but it's actually slightly different. And there's a formula which is not particularly complicated, but I figured you didn't want to actually see the formula. So I've got pictures instead. There's three components that go into calculating it. The first is the rock rigidity. So this is a picture of a granite. You might have that in your kitchen, in your countertop, and that's a relatively rigid rock. And you can compare that to a rock like this, which is a mudstone or a shale, and it's relatively weak. So imagine if you're straining or breaking the granite, it's going to make a larger snap when you break it. So a more rigid rock equals a larger magnitude earthquake. The other thing that matters is displacement. So this image on the top is from the San Andreas Fault, and this part of it called the Carrizo Plain. And you can see there's actually a river channel that's offset by about 3 meters right here. That's a pretty big displacement. And then in this farm field down here, let's say it's about 30 centimeters. So there's an order of magnitude or more difference between an offset between those two. So the larger offset equals a larger earthquake. And then the last thing that matters is the rupture area. So if the fault can rupture over a really big area, so for example, this 1960 earthquake right here, this pink zone is showing at least part of the area over which the fault moves. That entire area moved in a single earthquake. And this is actually the largest earthquake ever reported, magnitude 9.5. So a large rupture area generally equates to a really large earthquake, and a smaller fault rupture area is a smaller earthquake. So as it turns out, let's talk about what it means when we go from one magnitude to another magnitude, either in the Richter scale or this moment magnitude scale. It equates to a 32 times increase in the amount of energy released, going from, say, a magnitude 5 to a magnitude 6. That's a lot. So you'll see this diagram a lot when you're building earthquake intensity. And there's a lot going on here. But essentially down at the bottom, we're showing magnitude 2 earthquakes. And then the width of this feature here in the middle is telling you something about the number of earthquakes that happen every year. So there's a million magnitude 2 earthquakes that happen every year. Probably there's already one that's happened as I've been talking tonight. So they're happening all the time. But nobody notices them. It's really nothing you would notice unless you have a seismic instrument. 100,000 magnitude 3s every year, 12,000 magnitude 4s, 2,000 magnitude 5s. Now we're starting to get into light earthquakes, some property damage, and something that people would notice. 200 magnitude 6s, 20 magnitude 7s, and now we're starting to get into earthquakes that you may have heard of. These are large earthquakes that were damaging, killed a lot of people. So we're starting to get into shaking that's significant enough to cause damage. I think I'm briefly mentioning all 3 of these earthquakes. Only 3 magnitude 8s a year, and less than 1 magnitude 9. In fact, in the last, in recorded history since 1900, there's only been 5 earthquakes of magnitude 9 or greater, so they don't happen very often. And then over here, we've got sort of amount of energy released, but I'm going to try to do more of a graphic demonstration. So I have an assistant. Riley, would you like to come up and help? Okay, big reveal. Go ahead. Spaghetti. So we talked earlier about breaking a stick. Okay, so instead of a stick, we're going to break spaghetti. So let's say that breaking 1 strand of spaghetti, not yet, is a magnitude 5 earthquake. Okay, all right, Riley, go ahead now. Excellent. Okay, so that's 1 strand of spaghetti that just broke. Did you feel it? When you broke it, did you feel a vibration? No. Okay. Okay, so then a magnitude 6 earthquake is breaking 32 strands of spaghetti. So I actually counted out 32 strands, and Riley is going to break it for me. So we'll have to sweep up afterwards. And so magnitude 7 is 32 times 32 strands of spaghetti. That is about 1,000. No, I didn't count them. I weighed them. I weighed 32 and then multiplied it by 32 and weighed out that much. Should we break it or not?
Yeah.
Maybe we can have a challenge afterwards, see if anyone can break it. So it takes additional energy being put into the system to, break that many strands of spaghetti, and then it would actually, Riley would feel it in our hands. She did it. Okay, so that was 32. This is 1,000 or so strands of spaghetti. That's what a magnitude 8 would look like. Imagine a Parmesan wheel and trying to break that much spaghetti. And magnitude 9, are you ready? Yeah.
That's easy.
You can break a wheel? I'm very impressed.
With this guy.
Anyway, so maybe this gives you a sense for how much, it sounds like not that big a deal, right? A magnitude 6 to magnitude 7, or a magnitude 7 and a magnitude 7.1, but it really is a big deal. There's so much more energy that's released at each level. Okay, so that's the sciencey way that we describe the magnitude of an earthquake. And it also tells you the magnitude of the earthquake at a point at the epicenter, not the epicenter, the hypocenter of the earthquake, right? But it doesn't really tell you what you're going to experience, because if you're very far away from the hypocenter, you're not going to feel much shaking. So this is not very practical in terms of thinking about hazards. And so what we use instead is this scale. And you may actually have encountered this before, the modified Mercalli intensity scale, or the Mercalli scale. And it has to do with the experience that people have or buildings have during an earthquake. And it uses Roman numerals. And, for example, magnitude 4 is felt indoors by many, outdoors by a few. Dishes and windows are disturbed, and so on. And you end up producing a map that looks like this. So this is a map of the Northridge earthquake in the LA area. This is the epicenter right here, and you can see the most intense shaking was actually to the north of the epicenter. And it reached about a magnitude 9 or so, which is damages great, substantial buildings with partial collapse, buildings shifted off foundations. And then as you get away from the epicenter of the earthquake, the damage is less intense. It's not a perfect circle. You might expect this to be perfectly symmetrical, and it's not, because it has a lot to do with the substrate. So if your building is on bedrock versus if your building is on material that's been filled in, it'll make a difference in terms of the shaking intensity. And sometimes it can be directional. If the fault sort of moves in one direction, it might be asymmetric that way as well. Okay, so this is a good transition into the next part of the talk, which is what makes earthquakes so deadly. And it does have to do with the shaking, and maps like this are very useful. So there's a saying, which is that earthquakes don't kill people, buildings do. If you were out in a field and there was a magnitude 9 earthquake right next door, you would certainly be thrown to the ground. But unless a tree fell on you, you would be fine, because again, these chasms don't open up and swallow people and close up afterwards. You would probably be seasick. It would be a really terrible experience, but you would survive. It's things falling on you that kill you. And I found a not pretty graphic, but this is the best I could do, from a 1992 study where they tallied earthquake deaths since 1900. And you can see that 3/4 of them are the result of collapse of either masonry, timber, or reinforced concrete buildings. Now, this is 1992. Since 1992, we had the Boxing Day earthquake, 2004, which killed 300,000 people in a tsunami, and the Tohoku earthquake, which killed another 18,000. So if we redid the study today, there would be a slice of the pie for tsunamis. But nonetheless, the point is that buildings are what's dangerous. So I'm going to show you some pictures from the recent earthquake, it was about a year ago in Turkey, of collapsed buildings. So this is an example of a building where the front fell off. A lot of times buildings will have sort of masonry facades, and if they're not properly reinforced, they can actually just sort of peel off the building during an earthquake, particularly depending on the shaking direction. Which is, of course, dangerous if you're trying to get out of the building. You don't want to stay close to the front of the building in case it collapses. Here's another example. This building is actually a result of shear failure of the base layers of the building. So a lot of times on the ground floor, you have a carport or you have a big lobby, and so you haven't reinforced the walls in the same way that you have at the upper levels of the building. So in this case, the ground level sheared and the whole thing sort of slid over to the side. And here's the worst scenario, which is where you're building pancakes. That's the word they use for it. So the walls collapse and the floor is just sort of pancake on top of each other. And this one is particularly easy to see what happened, because you can see this part was better reinforced. And so that's the original height of the building. And this is an example from actually Mexico in 1985. There's an earthquake there that was very particular in that only buildings between about 6 and 15 stories were destroyed, and only in certain parts of the city. This has to do with what we call the resonant frequency of the building. So very long wavelength shaking will shake taller buildings and leave the shorter buildings untouched. And very high frequency shaking may destroy fewer story buildings, but leave the larger buildings untouched. So in this particular earthquake in Mexico City, it was built on a space and fill, and it just hit the right frequency for these sort of mid-range buildings and collapsed them preferentially. And so we'll talk about it later, but one of the really important things is knowing what kind of earthquake you're likely to have. What's the magnitude that you're likely to have? Because the way you engineer depends on the magnitude of the earthquake. So buildings are bad or dangerous, I guess, in earthquakes. I wanted to talk about some of these other slices briefly. So fires are a major problem in earthquakes. 1906 in San Francisco, for example, largely burned the city. And we haven't fixed it. This is from Kobe in 1995, where big parts of the city burned after the earthquake. And partly that's because gas mains are ruptured and also because we can't get there. So firefighters can't get to parts of the city well and to put out fires. Landslides are also an important, in certain parts of the region, an important hazard associated with earthquakes. This image is from the Gorkha earthquake in Nepal in 2015. Nepal is a country of very steep slopes, and so when you shake them, they will often collapse. So this is a before and after showing this farming village, which was destroyed. So I mentioned briefly, I think earlier, liquefaction. So liquefaction is when you have ground that's saturated with water, and during the earthquake, the water actually pushes apart. It basically turns the ground into quicksand. And buildings can sink. And so this building is intact. It didn't actually suffer shear failure the way the example I have from Turkey did. It actually basically sank into the ground during the earthquake, during the shaking. And you can see this building did, and this one as well, but to a lesser extent. And then I mentioned tsunamis. So again, if this survey was redone after 2004 or after 2003, we would have a bigger slice of the pie here for tsunamis. This is an image from the 2004 Indian tsunami earthquake. That was a really big earthquake, but it produced this gigantic tsunami that swept across the Indian Ocean and killed, said, about 300,000 people. And then, of course, I don't know if this actually was counted in the study, but there's everything that happens well in the aftermath of the earthquake. After the tsunami's over, after the shaking is stopped, then there's the humanitarian crisis, right? So people are without homes. Maybe it's cold, they don't have adequate sanitation or access to food. So this is an image of a camp after the Haiti earthquake in 2010. Okay, so that's in general what makes earthquakes deadly. I don't think I need to convince you that earthquakes can be very deadly. But what's interesting is that some are less deadly than you'd expect. So I'm now going to show you a map of the 6 largest earthquakes that have happened since 1900. So the largest, I think I mentioned briefly, was in 1960 in Chile, 9.5. We probably can't get much bigger than that because the size of the magnitude of the earthquake is limited by the size of the fault that ruptures. And so we're never going to get a magnitude 10. I don't know if anyone's calculated theoretical limit, but 9.5 is pretty close to it. The 1964, this actually was Good Friday earthquake, so we just had the 60th anniversary. The Tohoku earthquake in 2011 killed people with the tsunami. The Sumatra earthquake in 2004, also a lot of tsunami deaths. And then there was a relatively large earthquake in Kamchatka and in Malé, Chile in 2010. And you can see the number of deaths vary widely from 300,000 to as low as 130 in Alaska. And so the size of the earthquake doesn't necessarily equal a lot of deaths. So now let me show you the 6 deadliest earthquakes that happened since 1900. So Tangshan in China, magnitude only 7.8. I mean, not only, it's big, but it's not as big as some of the ones we just looked at. The Sumatra earthquake, Haiyuan in China, Haiti. This one is in Turkmenistan. And then there's an earthquake in Messina, Italy. And with the exception of the Sumatra earthquake, all of these deaths essentially are the result of buildings collapsing. And they range as low as magnitude 7. So I'm going to talk in just a tiny bit more detail about 3 earthquakes. And funny phrase is the good, the bad, and the ugly, but we're going to go in the opposite direction. So we're going to start with the ugliest earthquake, which was Haiti, and then talk about Tohoku, and then about the Malé earthquake. And just look at the difference in magnitude between these two earthquakes, which happened just to think about 2 weeks apart, and the difference in the depth. So starting with Haiti, and more of my work is actually in tectonics, so I just wanted to sneak in a couple of plate diagrams here. So what happened in Haiti, this is the Caribbean plate, and it's moving to the east relative to the North American plate to the north and to the South American plate the south here. You can see these purple lines, these are strike slip faults. The arrows show the direction of plate motion. And over here, the Atlantic plate is actually being subducted underneath the Caribbean plate, and it produces some volcanoes and also some earthquakes out here in this part of the Caribbean. But yeah, this is called the Enriquillo Fault, and the earthquake happened just a little bit off of it, actually just slightly north of the Enriquillo Fault on a blind frost, so a fault that we didn't realize actually existed before it happened. And there was some historic seismicity, but not a lot. And really, the earthquake was magnitude 7, which is a big deal, but we obviously have a lot bigger earthquakes that happen all the time, but they don't cause as much damage. So what happened in Haiti is that buildings collapsed. So here's an example of a neighborhood that was almost completely destroyed. And it had a lot to do with a lack of poor building codes, a lack of enforcement of building codes, and a lack of people's abilities to actually engineer, afford the material and engineering costs to build appropriately for earthquakes, and with a relative lack of understanding of the threat. There's threat from hurricanes all the time, but earthquakes are much less frequent. So they didn't engineer appropriately. Now, it affected poor neighborhoods, obviously, but it also affected even the presidential palace, for example. So here's the presidential palace before the earthquake, and here's what it looked like afterwards. And then here's some close-ups of the building. You can see that there was shear failure here where the columns didn't adequately support the roof above it. And here's an image of some of the corroded rebar. And I have to say, this does not look all that different to me than from the Gardner Expressway. So, maintenance and engineering are, okay, so that's what happened in Haiti. And then there's a humanitarian crisis afterwards as well, but a lot of people died in a relatively low magnitude earthquake. Next example is this Tohoku earthquake in Japan. So again, the plate diagram. This is what we call a triple junction. So the Japan Trench is subducting underneath the Eurasian plate, and the Philippine Sea plate is also trapped in here as well, and it's also subducted. So you get kind of double subduction zone here. So Japan is well prepared for earthquakes. They are very, very aware. I think probably the same level as California, if not more aware of earthquake hazards. And so they certainly anticipate earthquakes, but they didn't anticipate just quite how large the Tohoku earthquake was going to be. It was just a little bit larger in terms of its magnitude, and the tsunami it generated was just a little bit higher than they had planned for. And so most of the deaths weren't from buildings collapsing, but they were from the tsunami overtopping the seawall, which you can see really nicely here. And so it surprised everybody by overtopping the seawall, rushing in, and of course it also inundated the Fukushima power plant, which led to release of radioactive material into the ocean. So the tsunami generates when an earthquake happens offshore underwater. It displaces water, and a tsunami wave rushes in 2 directions. So it rushes usually towards the land that's nearby, and they'll have very little warning, maybe as little as 10 minutes, maybe 20 minutes before the tsunami hits. But the tsunami also travels in the opposite direction. And so here's an image of the tsunami heights heading out across the Pacific. Here's Hawaii, it gets hit in every direction. But you can see that it traveled all the way across the ocean, and I think there are 3 deaths around the world outside of Japan as a result of this tsunami, but really not very many compared to, for example, the 2004 Indonesia earthquake. And that has a lot to do with early warning systems. And so there's a series of buoys that are placed around the Ring of Fire, around the Pacific Ocean. A boat wouldn't detect a tsunami in the open ocean because of a very long wavelength, but buoys can do that. And so then they can get warning to places around the Pacific Ocean and tell people to take care and to evacuate. And then I'm just going to talk briefly about the Chile earthquake in February of 2010. Magnitude 8.8, so it was the 6th largest in recorded history. And it happened just north of where the largest earthquake ever in recorded history happened here in 1960. And it has a really pretty large rupture area. So it was a really big earthquake. And to give you a sense, so like I said, it happened just within a week or two of the earthquake in Haiti. This is a map of the rupture. So the fault rupture, the colors show you how much the earth moved on either side of the fault. So where it's red, we have 7.5 meters of displacement, and it sort of tapers off to the side, and it's got this typical sort of oval pattern to it. That little black box right there is the equivalent to the rupture area of the earthquake in Haiti. So this is the same map for the earthquake in Haiti. And just to get a sense, remember it's about, not quite, but almost 1,000 spaghetti strands compared to one spaghetti strand. And you get a sense for just this difference in scale between these two earthquakes. But only 525 people died. And so this is an image of a building that was destroyed in that earthquake. And when I was Googling images for destruction associated with this Mali earthquake, this is the only one I found. I found this building from 8,000 different angles, but it was always the same building. And it turns out that only 4 buildings collapsed in this earthquake. That's it. 40 more were damaged, which is less than 1% of residential buildings. So the buildings, more or less, were intact. So they investigated and found that of the buildings that did fail, they could explain why they failed. It's either because they didn't adequately characterize the material that the building was built in, what the substrate was, or they had just made a mistake in the construction. And they changed the building codes as a result of this. And so in theory, an earthquake like this, a magnitude 8.8, could be completely survivable. They could completely engineer buildings that do not collapse in the earthquake if they have a very good understanding of the magnitude of earthquake that they're expecting, and if they're able to create and enforce building codes. So that's the good. So let me get to the last part of this, or almost last part of the talk, which is predicting earthquakes. So if we're going to engineer buildings, we need to know what kind of earthquakes we can expect. Okay, so I'm about to make an earthquake prediction. This is magic. Ready? So for an earthquake prediction, you have to have 3 things: a magnitude, a location, and a date. So I'm going to make the prediction that we're going to have a magnitude 7.7 earthquake in Mississauga in 15 minutes at 8 p.m. Right? Okay, so I'm wrong. That's not going to happen. I mean, I guess it's possible, but extremely unlikely. So we can't do this, and we probably never can. We can perhaps, I'll show you in the next slide, but we can perhaps see some precursor to earthquakes, like the sort of winding up to an earthquake happening. But knowing the exact moment when it's going to happen is probably something we can never do with science. And you may have heard, this is a cute one, you may have heard that animals behave strangely before an earthquake. And it's possible, actually, that there may be some, imagine if you're breaking spaghetti or breaking a stick, sometimes you get little crackles before the main break happens, right? Like the outer part of the stick starts to break a little bit. And that may happen with earthquakes as well. You may get a few little crackles, a few called microseismicity, small earthquakes that happen early on. And so it's possible that animals could detect it. It's also, there's a study in China where they looked at the release of radon gas. So these little crackles created pathways for radon gas to escape. So it's possible that we may find precursors at some point that do a better job of telling us when we're winding up for an earthquake. But again, the exact moment of the earthquake isn't something we can predict. Okay, so I'm going to make another forecast. So I'm going to say that sometime there's going to be a magnitude 2.5 earthquake in, let's say, California in the next 30 days. So I'm right about this one. I'm 100% sure that that's going to happen, because this is what's happened in California in the last 30 days. It's a seismically active region. Magnitude 2.5 isn't really very big. There's somewhere between 100,000 and 1 million of those that happen every year. So certainly something like this is going to happen in California. So I'm correct. But is this useful? No, it's definitely not a useful prediction. Right? And so we want to find something that's in the middle, right? Something that is accurate, but also something that people can use when they're planning buildings, for example. So I'm going to stay with California and sort of try to quickly walk you through forecasting earthquakes. So we don't predict earthquakes, but we can forecast them. We can talk about the probability of an earthquake of a certain size happening in a certain region in a certain period of time. So this is an example. So California and like I said, Japan are 2 places in the world where they've done a lot of work on this. And so I'm just going to give you this example from California. So the first thing they need to do is know where the actual faults are. And that's harder than you would think. A lot of them, if they're not active, they may actually be sort of invisible to us. But most of them are active in California. And so here they are. And, you know, this is the San Andreas right through here, but you can see there's a lot of faults that are parallel and some that are even orthogonal to it. So there's a lot of faults in California. So we have to know where they are first. And then the second thing is we have to model how they move. So imagine that you take California and you slice it along all of those faults. You have to apply some kind of physics to how those blocks slide past each other, right? They're going to stick to each other in some way. There's going to be elastic strain that's accumulating. And this isn't the best picture to illustrate it, but it's the best I could find. So on the left is somebody who's used all those little sliced up blocks and applied some physics, and they're testing as to whether or not they've made a good model. And so in red are actual data, it's GPS data, just like the GPS you have on your phone, but it's more accurate. And in this blue or purple color is their model. And then they're looking to see how close their model matches reality. And so the figure on the right is the residual. So it's when they subtract those two arrows from each other and see what's left. And the ideal is that they have just little tiny pinpricks because the residual is very, very small. So this is an example of a successful model where they've applied physics to these fault blocks to come up with a solution. Problem with this is it doesn't look at history at all. So the next thing is they need to build in a longer term fault behavior. And that's where more of my research actually comes in. So one thing we do, and I'm jumping to a different part of the world, but I'm doing this because it's a paper that one of my students, former PhD students, worked on, is we can find faults. So this is an example of a fault that's cutting a quaternary surface. So this is a river terrace, Q1 here, and in the same Q1 over here, it's displaced by this fault. And then we can measure the age of that displaced surface, and that allows us to calculate a fault slip rate. So how fast is that fault moving? And we do that for a series of surfaces. So there's actually 4 different river terraces of different ages that are offset along this fault in Argentina. And then we end up producing a diagram like this. And I just want you to look at the red data right here. This is the actual slip rate on the fault itself. And then this Q4, Q3, Q2, and there would be a Q1 up there. Those are those different offset surfaces. And we're plotting age versus the amount of displacement. And then you can see these dotted lines here are the fault slip rates. And so approximately this fault over the long term meaning 45,000 years, has experienced a slip rate of about 0.5 millimeters per year. Okay? So we collect data like that for faults, like many faults in order for it to be useful and relevant. So it's this painstaking work that a lot of people have done to try to figure out what fault slip rates are. And then you also want to know something about the recurrence interval. So you know how fast the fault is moving, but you don't know how sticky it is. So you don't know if you've got a lot of small earthquakes that release that strain or a few big ones. And so to look at that, we do something called paleoseismology. So you dig a trench across a fault that reaches the surface. And the scientists here have, this is a photo I took in Salton Trough, so in Southern California. And they've made a grid here and they've highlighted important features, including things like charcoal, so they can use C14 data to dating to try to understand the age of this material. And then they create a diagram that looks something like this. So this is a map of the trench wall. And they're looking for places where they see other faults that cut certain units. So this one, for example, cuts the pink, the red, the yellow, and the blue. And then when it's where it's truncated by another unit. So these were here before the earthquake happened. This unit was deposited afterwards. And then you try to date those two, and that lets you bracket the age of the earthquake. And so you create an earthquake record. So then you can figure out how often earthquakes are happening, and then you can try to get at how large those earthquakes are. And then you put it all together, using a probability model. And the end result is something like this. This is a really amazing map. And this is version 3. They're working on a version 4, which is updated, but it hasn't been released yet. And so all of these little sort of fence-looking things, those are individual faults that they've done work on. And most of them are vertical, but some of them are dipping towards or away from you as a viewer, and so they get that kind of more stretched out appearance to them. And then they're color-coded by the likelihood of each of these faults hosting a magnitude 6.7 earthquake or greater in the next 30 years. And they chose that because the Northridge earthquake was a 6.7 magnitude, and that sticks in the mind of a lot of Californians, and because a mortgage is typically 30 years. So it makes sense, like something like Northridge, would it happen to you in the duration of the period that you're going to own this home? That thought that was a way to sort of make the risk seem more real to people. Right? And so pink means that there's a 100% chance of magnitude 6.7 happening in the next 30 years. So right down here in the Salton Trough in Southern California. Red isn't great. There's a 10% chance of an earthquake happening in the next 30 years. Blue, is fine. And then they've color-coded the faults, and then they've also colored the zone around it because the shaking will transmit to the region. So this is something that is very useful in terms of building codes and in people making individual decisions. So one more thing to say about earthquake prediction is, can we give people some warning? So not predicting an earthquake, but after an earthquake happens, can we give people some warning? And there's a project in California called Shape Alert, and their motto is seconds matter. And that's the idea, right? That even a few seconds warning gives people a chance to, for example, get under heavy objects. We would all die for that table right there if our Shape Alert app told us that there's an earthquake coming. Or it gives us a chance to shut off gas mains, for example, or to stop trains. And so the Shape Alert, the way it works is that an earthquake happens, and a sensor will receive the information that earthquake has happened. It will start to shake. And very quickly, they can process that information to estimate the epicenter and the magnitude of the earthquake. And then they make a really quick and dirty calculation about how much shaking people are going to experience and when. And based on that, they send out a warning, and it literally comes to people's cell phones. So I have the Shape Alert app on my phone. I attended a lecture recently about it and downloaded it during the lecture. And it's not available in Canada now, but it actually will be relatively soon, I think in the next year or something like that. So it's also super fun. And you can also contribute. So if your phone is plugged in and lying flat during an earthquake, they can actually use the data from your phone to add to this sort of virtual seismic network. So this is really promising, the idea that you can give people a few seconds to even a minute or two of warning before an earthquake happens. Okay, so what about Canada? So here's a map of all of the earthquakes that have happened since 1627 in California, all the ones we know about. The farther back in time, the less able we are to accurately record and locate these earthquakes. And not surprising, there's a lot on the West Coast, including this one right here. That was a magnitude 9-ish, we think, earthquake that happened in year 1700. And that's a whole interesting story that I don't have time for tonight, but that's a really big one, a megathrust earthquake. But there's a lot of seismicity over in Eastern Canada as well. Particularly, you see this line right here. This is the St. Lawrence seismic zone. And then this is the Ottawa Graben right here. And so this is a place where there's ancient faults. So these are scars from old tectonic episodes. And they're not on a plate boundary, but they're experiencing what's called far-field stress. So the plate itself is being stressed on its edges. And that strain is accumulating a little bit in the interior of the continent. And where it's going to actually rupture is a place where the rocks are already weak. And so the seismic activity gets sort of concentrated in all these old tectonic scars. And just keep your eye on that little guy right there. This is a seismic hazard map for Canada. And again, you see it's red, which is bad over here on the West Coast, but there's still significant hazard over here on the East Coast, and you can see Toronto right down here is sort of between the orange and the yellow. So we're certainly not like the prairies, in a very low seismic region. And then zooming in a little bit more, this is a paper the same guy I mentioned earlier, Jeremy Raimondo. He did a postdoc for someone at McMaster, Alex Peace. And this is some work they did on the St. Lawrence seismic zone on the Ottawa Graben. And here's the historic seismicity in our part of the world. And this right here is the 1935 Temiskaming earthquake, a magnitude 6.1. So that's the biggest that happened in Ontario. It's the biggest that happened, in Quebec as well. And here's a locality intensity map for that earthquake. So it was in Temiskaming, and the shaking got up to 7, right in the vicinity of the earthquake. And you can see in Toronto, we were at a 4, which, as a reminder, is felt indoors by many, outdoors by a few, and dishes and windows are disturbed. So that's what, so just shows you that beautiful map of California, right? We haven't done that kind of work in Eastern Canada because the overall risk is lower. We're not riddled with faults the way they are that are constantly popping off the way they are in California. And so the risk is lower for us in general. But we don't really know what it is until we do that work. So this is a case for funding academics to, go out and study the slip rates on faults, to locate the faults, and to do the kind of work that they've done in California, so that I can give you a more accurate assessment of what the hazards are in Toronto. But I can say we don't have faults underlying us in Toronto. They're, closer to Ottawa or to Quebec, or sorry, Montreal. And so those could generate earthquakes of magnitude 7, maybe even magnitude 8. And so we would feel shaking associated with them in Toronto. And I would say the scarier part is that we're just not prepared for it. So it wouldn't be a lot of shaking, but we haven't prepared in terms of our building codes, and many of us personally wouldn't know what to do. So the last 3 slides, I want to talk about what you would do. So here's a picture of the gardener. So we should fix that. That's the first thing to do. But here's some advice, and I think a lot of this is good for any kind of disaster, so it's something you might as well get started with. So develop a family emergency plan. Riley, let's put that on our list. Okay. Prepare and organize supplies, secure top-heavy furniture. So for example, my kids were little, we strapped all of the bookshelves to the wall so they wouldn't pull them over on themselves, so that's something you can do. Practice drop, cover, and hold on. Know how to turn off gas valves. That's a great idea. Know what's in your house. Make sure that you have appropriate insurance. And then these last 2 have to do more with policy and with building codes, which is maybe beyond our control, but perhaps it's something that you can think about, sort of civically active. Okay, so if you're in an earthquake, either in Toronto or if you're traveling somewhere else, again, this isn't going to happen, but what you should do is really simple: drop, cover, and hold on. So you basically it's falling objects that kill people, right? So you get under the heaviest, sturdiest object that you can find, and you ride out the earthquake there. And if you happen to be in a tsunami-prone region, well, that's really bad. And the only thing you can basically do is just get out of the way. And you don't need to wait for tsunami warnings. If there's shaking, just get to higher ground as soon as you can and stay there, because tsunamis can come out and in for a very long period of time. Okay, so hopefully you feel a little bit more prepared for an earthquake now. Like I said, I don't lose sleep over an earthquake in Toronto, but I think some basic precautions would be a good idea. What you're probably not prepared for, however, is the possibility of San Andreas 2. Apparently they're threatening to release this movie in the next couple of years. Maybe you will be prepared because now you know a bit more about where they exaggerate what's realistic. But anyway, it might happen, so hold on. Okay, thank you very much.
I have a granddaughter at the UBC. Keep joking with her, say, always keep a bag ready, a safety bag ready. Is that advised there?
Yeah. Yeah, I think so. My sister, oh, sorry, the question. Yeah, so the question is, so if you have a loved one who's on the West Coast in the Pacific Northwest at UBC, for example, what should you tell them? Should they have a bag ready to go, and so on? I was just gonna say, I have a sister who lives on Anacortes Island in Puget Sound, near Seattle. And she asked me, actually, my mother asked me this question about her. And they actually, they make tsunami inundation maps. So you can actually check your location, whether or not you'd be, inundated if there was a tsunami. So the megathrust earthquake scenario on the West Coast is that there would be an earthquake offshore. And so it would have to make its way through all of the islands before it hits Vancouver. And so the tsunami run-ups in Vancouver aren't particularly high. And it's a relatively mountainous terrain, right? And so it doesn't take much to sort of get above the inundation zone. That's what I told my mom anyway about my sister. And it is a city, as far as I know, that does a good job. Like they do, I think the Great Shakeout is great. I think it's called the Great Shakeout, but they do sort of earthquake drills, and stuff. So there's good awareness. But I think looking into building the code of the particular building that she's living in, and doing the sort of basic preparedness steps, and maybe looking at the tsunami maps is a good idea.
Okay. Good advice. Thank you.
Okay.
You
you may explain before, but I just want to make sure that I get it properly. So about the prediction, is the prediction based on the previous experience or based on the measurement that they did about like the type of this?
Yeah, so the question is, when we're doing earthquake predictions, is it based on previous earthquakes or is it based on other measurements? And the answer is the best predictions are using both, and they're building them all into the model. We talk a lot about recurrence intervals. So, when was the last earthquake and how large was it? And then we look at faults where they haven't, we talk about them being overdue for an earthquake. And so the Pacific Northwest is essentially overdue for an earthquake because the last big one was in 1700. And since then, we've built up a lot of strain. Or the Southern San Andreas is another place where it's been, I'm going to make this up, I think about 250 years or so since there was a major earthquake. And given the historical frequency, the frequency that we've measured over geologic time, it seems like it's overdue. But this is the problem with predicting earthquakes is that they don't behave perfectly, right? They don't go off exactly every 150 years. Sometimes, you might only have a short interval between two major earthquakes, and sometimes the strain is building up for a lot longer. And so, yeah, I mean, basically the best earthquake models are going to build in as much data as they possibly can, including, as I mentioned, the sort of modern block modeling and the record. But, they're only models, and what actually happens could surprise us by being larger or by being smaller or by being more frequent than we expect. I think that's hard for people to get their heads around, right? And it's not that different from, I don't know how many of you are planning to see the eclipse, but, I've started checking the weather forecast for the 8th already, and, it's a bit premature, right? Because things can change. So it's a little bit like that. We can't predict what we can forecast. We just build in as much information as we can to do as good as we can, but it still might rain on the day of the eclipse, despite our best efforts.
Does hydraulic fracturing cause earthquakes, or like how is that studied? Really on its first one.
Yeah. So the question does fracking produce earthquakes or hydraulic fracturing? And yeah, it absolutely does. There are very clear studies that, and particularly I think it's where you have injection wells. So that the science is that if faults are, so you've got a fault, a break in the rocks, and you're accumulating strain, right? So the rocks on either side are moving, and it's essentially friction that is keeping it from rupturing in an earthquake, right? And so when you inject fluid, you're increasing the fluid pressure, and so you're essentially pushing the two parts of the fault apart from each other, and so you're reducing the friction that's holding them together, and so you can trigger an earthquake. So you're triggering an earthquake. You're not creating an earthquake that wasn't going to happen eventually, but you're maybe making it happen sooner because you're sort of releasing that frictional tension across the fault plane sooner. And yeah.
Well, wouldn't that be a good thing? Like, wouldn't that help then maybe prevent a big one by like creating these little ones?
Mm-hmm. Yeah, I think
there was that tension. Is that the logic?
And I feel like there might have been a Michael Crichton novel or something. Okay. But yeah, I mean, in theory, like if you were worried about a really big fault, maybe you want to like just pepper it, with smaller earthquakes that sort of slowly release the tension. The problem is like, yeah, like we don't know what we're doing well enough to do that, and so we could easily trigger a larger earthquake. I don't know if you know Smeke Liu in my department, but she actually studies this stuff. She models earthquake rupture and earthquake interaction. So one earthquake can actually increase the stress in the region right around. So you release the stress where the earthquake happens, but it can increase the Coulomb stress around the edges of it, and that can trigger additional earthquakes. So yeah, I don't know. People talk about that, about the potential for reducing serious earthquakes, but we're not there. I would be very worried if somebody started monkeying around with that.
Question on the chat line. I have to speak very loudly. Elizabeth, can you hear me in the back?
Yeah.
The question is, what is more hazardous, a deep or a shallow earthquake?
Mm-hmm. Yeah, so a shallow, so it's more complicated than just a deep or shallow earthquake, right? But a shallow earthquake is closer to the surface, and therefore the shaking that you feel immediately adjacent to the epicenter is greater. There's a lot of other stuff that goes into it, but a shallow earthquake is more dangerous. category. Yeah.
Any other questions?
What precautions could nuclear stations take in order to like prevent any damage from an earthquake?
Yeah. No.
What was the question?
Oh, sorry, the question, thank you. The question is what precautions could a nuclear power plant, for example, take to prevent damage in an earthquake? So the example in Japan, the Fukushima power plant, that was, they had built seawalls to prevent, inundation, and they weren't high enough, so building a higher seawall would have helped in that case. I don't know. I mean, I looked a lot at building engineering when I was, researching this talk in general. And there's good ways to build buildings that survive earthquakes. It has to do with essentially cross bracing of walls or building what they call shear walls. And so they can apply that to the nuclear power plants. And I imagine that fail-safe, things that just shut down, the power generation as soon as an earthquake happens will help. And then also, I think understanding how large the earthquake is likely to be is a really important part of the engineering. But yeah, I don't know. That's certainly a very, very important thing to get right. Yeah, and the student, I've had his name up here twice, Jeremy Raimondo. He's actually now working for I'm not sure I'm going to get the right name, but it's essentially the agency in Ontario that looks at siting power plants. And they also look for faults. So you don't want to build a power plant on a fault. That would be a really bad idea. So locating the faults and understanding how active they are and siting them in the right place is just is part of that story as well. Yeah, thanks. Good question.
Anybody else?
Okay. Well, thank you very much. I appreciate your attention tonight.
Thank you.
So that brings us to the end of our program tonight. It's also the end of our season, our academic season that we do the lectures. We will be lining up a lot of fascinating speakers and lectures for the fall 2024 lineup. So check in with us and come back. Good night, everybody.
Okay.